In the constellation Cygnus, about 1,470 light-years from Earth, there is a star slightly hotter and slightly brighter than our Sun. From 2009 to 2013, a NASA space telescope watched it continuously. The telescope was called Kepler. Its job was to find exoplanets. A planet passing in front of a star produces a brightness dip of less than 1%. Across 150,000 stars monitored at parts per million precision, Kepler had seen nothing like the dips at one particular catalog entry. Catalog number 8462852. The dips went as deep as 22%. They came at no regular interval. They had no clean shape, and we still cannot explain them. This is the cold archive. Kepler was launched by NASA in March of 2009. It was pointed at a single patch of sky in Cygnus and Lyra and instructed not to move. For 4 years, it measured the brightness of 150,000 stars, taking one reading every 30 minutes. The data volume was enormous. To find planets, Kepler's automated pipeline searched for periodic brightness dips, the signature of a planet crossing its star's face once per orbit on a fixed schedule. The pipeline was tuned for periodic events. Non-periodic events would slip through. In 2010, a Zooniverse citizen science project called Planet Hunters launched. Its premise: give the Kepler light curves to volunteers around the world and ask them to look. Human pattern recognition catches what the algorithms miss. Planet Hunters had thousands of contributors.
From a Planet Hunters talk forum post in 2011 by the volunteer Darryl LaCourse, a retired metallurgist in Washington state. Look at this one. The dips are huge. They don't repeat. I've never seen a curve like this in the catalogue.
LaCourse and another volunteer, Hans Martin Schwengeler, a Swiss software engineer, kept flagging the star in the forum. By 2013, the Planet Hunters team had collected enough data and modeling to start writing a paper. Tabetha Boyajian, then at Yale, took the lead. Boyajian and her co-authors posted the paper to Archive in September of 2015. It appeared in monthly notices of the Royal Astronomical Society in February 2016. The preprint title became the most cited line in the case. Where's the flux?
From Boyajian et al., 2016, abstract. We present a star, KIC 8462852, that exhibits periodic dips in brightness ranging from less than 1% to up to 22%. We enumerate a list of possible explanations, all of which face significant difficulties.
The paper laid out the dimensions of the puzzle. 22% dips require something at least a fifth the size of the star to occult it. The dips were irregular, no period. Their shapes were not clean planetary transits, and there was no detectable infrared excess in archival data. In October 2015, the journalist Ross Anderson wrote a piece in The Atlantic. He had interviewed Jason Wright, a Penn State astronomer, who pointed out that one hypothesis worth ruling out was a swarm of artificial structures partially occulting the star. The story went around the world in a week. Wright's published position, repeated then and since: the artificial structure hypothesis should always be the last hypothesis tested. He raised it specifically so that follow-up observations could rule it out. The follow-up observations rolled in over the next 3 years. In 2016, the Breakthrough Listen project at Berkeley turned the Green Bank telescope on KIC 8462852. They scanned for any anomalous radio signals from the system. They published a non-detection in 2016. No artificial radio signals. In 2017, Carl Lisi at Johns Hopkins led an infrared follow-up campaign using the Spitzer Space Telescope. If a recent population of comets or asteroid fragments was orbiting the star, their warm dust should glow at infrared wavelengths.
From Lisa et al., 2017. Spitzer, 4.5 micron observations of KIC 8462852 show no excess thermal emission consistent with a recent, dense, warm dust population.
The Spitzer result disfavored the recent comet swarm hypothesis. Not impossible, an older, cooler debris field could evade Spitzer, but the simplest comet models did not fit. The case for a circumstellar dust origin needed sharper data. In May 2017, KIC 8462852 began a new round of dimming in real time, while ground-based telescopes were watching. Boyajian and her team had set up the Las Cumbres Observatory Global Network to capture exactly this. The new dips were observed across blue, green, red, and infrared bands simultaneously. The result in the Boyajian et al. 2018 paper. The blue light dimmed measurably more than the red light. The wavelength dependence is the signature of fine dust grains, not of a solid macroscopic occulter. A swarm of artificial structures would dim all wavelengths equally.
From Boyajian et al. 2018, the observed wavelength-dependent dips are inconsistent with an opaque occulter and consistent with circumstellar dust grains of approximately 1 micron in size.
The artificial structure hypothesis was eliminated by the 2018 color photometry. The leading candidate became dust. But which dust, where, in what configuration, was still an open question. 3 hypotheses have survived the 11 years of follow-up. Each one survives most of the constraints. Each one fails at least one. We walk through them. Hypothesis 1. The original artificial occulter hypothesis raised by Wright in 2015. The premise: an array of large solid structures partially blocking the star. This was the press cycle hypothesis. It is also the cleanest one to test. The constraint that breaks it: solid structures occult all wavelengths equally. The 2018 multi-wavelength campaign showed wavelength-dependent dimming, blue more than red. Independent confirmation came from Deeg and colleagues in 2018. The artificial occulter hypothesis fails on color. Hypothesis 2, a recent comet swarm. The Boyajian 2016 paper proposed a population of cometary fragments produced by the breakup of a larger body, orbiting the star with a wide range of periods. The shapes would be irregular. The depths would vary. The behavior matches the Kepler curve broadly. The constraint that breaks it: the Spitzer 2017 infrared survey. A young, warm population of cometary debris would emit at thermal wavelengths Spitzer could detect. Spitzer found no such excess. Simple recent comet models do not fit. Hypothesis 3, the current leading explanation: circumstellar dust. Fine particles in orbit around the star itself, possibly in a complicated geometry, a tilted ring, a colliding fragment field, a slow asteroid disruption, with grain sizes of roughly 1 micron. The 2018 color photometry is consistent with this. The constraint that complicates it: the Kepler-era dips reach 22%. Sustaining a dust population dense enough to cause depth at that level requires a continuous resupply mechanism: colliding bodies, fragmentation, active dust production, that has not been independently confirmed. The dust hypothesis fits the color data, but not the full depth budget. A fourth possibility, an interstellar cloud between Earth and the star, proposed by Wright and Sigurdsson in 2016, explains some of the dimming but struggles with the sharp edges seen in certain dips. It is consistent with the color data, but constrained by the dip morphology. 11 years after the Boyajian preprint went up, the Las Cumbres Observatory still has KIC 846-2852 on a monitoring list. The dips continue. They are smaller now, most under 5%, but they have not stopped. The data archive grows. The artificial occulter hypothesis is eliminated. The recent comet hypothesis is disfavored. The interstellar cloud hypothesis is constrained. The circumstellar dust hypothesis is leading, but does not cleanly explain the deepest dips. The system has not surrendered a clean answer. What we know: KIC 846-2852 is an F-type main sequence star, mass about 1.4 solar masses, 1,470 light-years from Earth. It is otherwise unremarkable. There is nothing in its spectrum, its rotation, or its age that flags it as unusual. Only its light curve does. What we do not know: what caused the 22% Kepler-era dips. Whether the dust seen in the 2018 multi-wavelength campaign is the same population responsible for the deeper events. Why the dimming has continued at lower depth for 11 years. The Kepler light curve is public. The 2017 multi-wavelength campaign is public. The Spitzer infrared data is public. 11 years of ground-based follow-up monitoring is public. No proposed mechanism cleanly explains every dip. The star is still dimming. 4 years of Kepler data, 22% at maximum. 11 years of follow-up. No clean answer. Wednesday's case: November 24th, 1971. A man walks onto a Boeing 727 in Portland, Oregon, with a briefcase and a bomb threat. He demands $200,000 and 4 parachutes. He gets them. Somewhere over southwest Washington, he parachutes out the rear stair. 45 years of FBI investigation later, no one has identified him. D.B. Cooper, Wednesday, 8 p.m. Eastern. See you then.